Does Amendment 4 actually change how you install an electrical system? EV chargers, batteries, medical locations, fire safety and containment are just some of the changes that have landed in this version of BS 7671, the Tangerine book. So in this video, we're going to focus on those parts that actually affect you on site, what has changed, what those changes mean in practice, and where they're likely to catch you out. We've also created a free CPD on the updates to BS 7671, and I've left those links in the description. Traditionally, electrical installations were simple in terms of how they behave. Power flowed in one direction from the supply into the installation. Protection was designed around that idea. Fault current travelled back to the source, devices operated based on that expected path. And in systems like TNS, that behaviour was predictable. The earthing arrangement relied on that single direction of flow back to the source, but that is no longer always the case. We now have installations that can both import and export energy. Solar PV, battery storage, multiple sources of supply, all connected into the same system. So the installation is just no longer receiving power, it is interacting with it. And that has a direct impact on how the system behaves under fault conditions, including earthing systems like TNS, because the way the system responds can now depend on the direction of power flow. And this is where Regulation Group 551.7 comes in. This has been redrafted to deal with installations operating in parallel with other sources, and the key requirement now is that protection must remain effective regardless of the direction of power flow. So it is no longer enough to design protection for one direction, it has to work in both. That means overcurrent protection must still operate correctly, thermal protection must still operate correctly, and RCD protection must still operate correctly in all operating conditions. There are also now restrictions on how sources can be connected, particularly where RCDs are involved. So a setup that may have worked previously can now create problems. You can no longer just connect generation anywhere into the installation. A good example would be connecting generation onto the load side of a shared RCD in a split load board. On the surface, everything still looks correct, but under fault conditions, the presence of another source can affect how that RCD operates. If the device is not disconnecting all live conductors, including the neutral, it can end up in a situation where effective disconnection is not achieved, because current can flow in paths that the device was never designed to interrupt. So what used to be a common way of doing things now needs to be reconsidered. Regulation 551.7.2.1 now requires that generation sets are connected on the supply side of the protective device for the final circuits. So in simple terms, generation needs to be connected upstream of the circuit it is supplying. And importantly, this includes batteries, which are now treated as a generating set in this context, not just a load. There are also supporting changes around this idea. Regulation 536.4.202 has been redrafted and now includes coordination between protective devices, assemblies, and load control, such as load curtailment. So what does this mean? Well, the regulation is focused on making sure that the assembly itself is not overloaded. Traditionally, this was straightforward. You would select a protective device upstream that did not exceed the rating of the board. So if the board was rated at 100 amps, you would not protect it with anything higher than that. That still applies, but installations are no longer that simple. We now have multiple sources of supply, solar PVs, batteries, EV charging, all interacting with the installation at the same time. The question is no longer just what is feeding the board, it is what the board could see in total. The regulation now gives you 3 ways to stay within the limits of that assembly. The first is the traditional approach. Make sure the upstream protective devices does not exceed the rating of the assembly or anything inside it. The second is load curtailment. This is where the installation actively limits the maximum current demand. So instead of relying on the size of the protective device, the system controls the load itself. For example, reducing EV charging output when the rest of the installation is under demand. The third option is to make sure that the total connected load does not exceed the rating of the assembly. And this is where things tighten up. You are not allowed to rely on diversity here. Nope. You have to assume the worst case scenario. Everything on, everything contributing. So if you had a 100 amp board and 60 amps coming from the grid and another 60 amps coming from the battery or a PV system, individually that may look fine, but together that exceeds what the assembly is designed to handle. If load curtailment is being used, it must reliably limit the current to within the rating of the assembly, and diversity cannot be used as a substitute for that control. There is also a practical implication here. If total connected load is being used as a method of compliance, the regulations require a warning notice, clearly stating the maximum permitted load for that assembly. So anybody working on it understands that limit before adding to the installation. Regulation 521.5.1 has also been clarified around electromagnetic effects in ferromagnetic enclosures. In simple terms, if conductors carrying current are split across different entries into a metal enclosure, they can induce current into that enclosure. That can lead to heating and unwanted electromagnetic effects. So the clarification now makes it clear that all conductors of the same circuit should pass through the same opening. There are exceptions. A CPC can be run separately, and armoured cables or correctly terminated glands can manage this through their construction. But the principle is that the magnetic fields cancel out when the conductors are kept together. But keeping cables together is only one part of the story, because once those cables leave the enclosure and start running through walls or partitions, the risks change. And this is where Amendment 4 introduces something new. We have a new table, Table 52.1. This sets out the requirements for cables concealed in walls or partitions. What this does is bring much clearer guidance based on two key things: the construction of the wall and the depth of the cable from the surface. So instead of relying on interpretation, you now have defined requirements to follow. For example, where a cable is installed at a depth of less than 50 millimeters, additional protection is typically required, usually by means of an RCD. But once you go deeper than 50 millimeters, those requirements can change depending on the wall construction. And if the wall contains metallic parts, that also affects what is required. So this is no longer just about putting cable in a safe zone, it is about understanding the construction of the building and installing the cable accordingly. That same thinking carries through when you move outside. Regulation 522.8.10 deals with cables buried in the ground. Here the expectation is that the cable must incorporate an earthed armour or metallic sheath, unless it is installed in a conduit or duct that provides equivalent mechanical protection. And this is where Amendment 4 adds further clarity. Metallic or non-metallic underground conduits with a classification for impact and compression of N750 to BS-EN 50626-1 or BS-EN 61386-24 are considered to provide equivalent protection against mechanical damage. So if you're using ducting as your method of protection, it now needs to meet the N750 classification. And it is not just about protecting the cable. Its location must also be identified using marker tape or cable covers, and it must be installed at a depth that avoids reasonably foreseeable damage. And if you want to find out how deep you should bury a cable, I've done a video on that, and I've left links in the description. There is also a new table that sets out conductor classes, Table 52.4. So instead of just referring to conductors generally, the regulations now distinguish between solid, stranded and flexible types. For example, Class 1 and Class 2 conductors are rigid, where Class 5 and Class 6 conductors are flexible. And this matters when it comes to terminations, because different conductor types behave differently when they are connected, which leads into Regulation 526.9. This focuses on the connection of multi-wire, fine wire and very fine wire conductors. If these are not terminated correctly, the strands can spread or separate, so suitable terminals must be used, or the conductor ends must be properly treated. BS 7671 now includes a dedicated chapter for stationary secondary batteries, which is chapter 57. But what is a stationary secondary battery? A stationary piece of equipment, like a battery, is simply something that is fixed into place or heavy enough that it is not intended to be moved. Part 2 describes stationary electrical equipment as electrical equipment which is either fixed or which has a mass exceeding 18 kilograms and is not provided with a carrying handle. Then there's the term secondary battery. A secondary battery is one that can be recharged, so it can store energy and then release it back into the installation when it's required. And this is one of the biggest shifts in the regulations, because a battery is no longer just treated as a load within the installation. Regulation 570.1 defines it as a source of supply, so electrically it sits alongside the supply, not at the end of it. That matters because of how batteries actually operate. They charge, they discharge, and they can supply the installation as well as take power from it. So the installation is no longer just consuming energy, it is constantly exchanging it. Power is no longer moving in one direction. Because of that, Regulation 570.5 requires the battery to be selected based on how the installation behaves. That includes demand, load profiles, and any generation such as solar PV. So you are no longer just selecting a piece of equipment, you are deciding how that system is going to operate. The same applies to power conversion equipment, more commonly known as inverters. Regulation 570.5.2 requires it to be suitable for the battery and its application, taking account of the manufacturer's instructions. This is the equipment that controls the energy flow, and that flow can be in both directions, which then affects protection. Regulation 570.6.1.1.1 requires that bidirectional protective devices are selected where appropriate, so protection must operate correctly whether energy is flowing into or out of the installation. RCD selection is also affected. Regulation 570.6.2 requires a Type B RCD unless certain conditions are met. This is because of DC components from the power conversion equipment. So if you install the wrong type of RCD here, it may not operate correctly under fault conditions. Thermal effects also come into play. Regulation 570.6.3 requires batteries to be adequately ventilated because depending on the type, they can generate heat or even release flammable gases. Which leads us into location. Regulation 570.6.7.202 requires batteries capable of producing flammable gases to be installed away from ignition sources. And for dwellings, Regulation 570.6.7.203 points you directly to PAS 63100. So BS 7671 is setting the requirement, but PAS 63100 is giving you the detail on how to apply it in domestic installations. Isolation is also critical. Regulation 570.6.5 requires a means of isolation for the battery system, because even if you disconnect the main supply, the battery can still energize the installation, so you cannot assume the system is dead just because the main switch is off. And finally, labeling. It's back! Regulation 570.6.8 requires a warning notice to indicate the presence of a battery system. And you may need to install warning notices in different locations depending on the installation. A warning notice must be fixed at the origin of the installation, at each consumer unit or distribution board supplied by the battery, and importantly, at the metering position if that is remote from the consumer unit. So anyone working on the installation is aware that there is another source of supply. So this is not just about adding a battery to an installation, it changes how the system behaves, how it's protected, and how it needs to be approached when you are working on it. RCDs have not been replaced with something completely new, but the way you select them has changed. And this is where older habits can start to cause problems. Regulation 531.3.3 now makes it clear that the type of RCD must be appropriate for the characteristics of the load. That includes DC components and non-sinusoidal currents, which are now common in modern installations. So this is no longer a case of just fitting what has always been used. And the biggest shift is around type AC RCDs. These are now heavily restricted. They can only be used where it's known that the load current contains no DC components. In reality, that limits them to very simple circuits, things like basic resistive loads where the waveform is predictable. Everything else now pushes you towards type A as a minimum, and in some cases type F or type B, depending on the equipment being installed. This becomes critical when you start looking at systems with inverters, battery storage, EV charging, or anything with power electronics, because those systems can introduce DC leakage currents, and a standard type A device may not detect that properly, so it may not trip when it's supposed to. Section 536 has been redrafted to deal with how protective devices operate together. So selecting an RCD is no longer just about that one circuit, it has to work as part of the overall protection strategy for the installation, which means thinking about upstream and downstream devices, selectivity, and how the system behaves under fault conditions. So what does this mean, and how should selectivity look when it comes to RCD types? Okay, so a type AC RCD should not be installed upstream of a type A, type F, or type B, because the characteristics of the load downstream can effectively blind that type AC device, meaning it may not trip when it should. The same applies as you step through the types. A type A should not sit upstream of a type F or a type B, and a type F should not sit upstream of a type B, because each step introduces more complex waveforms, and if the upstream device cannot recognize them, it cannot provide protection. This is often referred to as RCD blinding. So you might have multiple RCDs in series, but if they are not coordinated correctly, the one you are relying on may not operate. EV charging has had some important clarifications that will affect how you design and install these circuits. One of the biggest changes is the recognition of RCDs incorporated within the EV charger itself. Regulation 722.531.3.101 now formally recognises these devices, in particular devices that provide both AC and DC protection within the charger, often referred to as RDCPDs. This is a big shift because previously there was a strong push towards installing external Type B RCDs. Now, if the equipment complies with the relevant standard, that internal protection can be relied upon. So in practice, that can simplify your installation. It can change board layout and it reduces the need for additional protective devices upstream. But it does rely on you understanding exactly what the charger is providing and confirming that it meets the required standard. So you cannot just assume all chargers are the same. There is also clarification around AFDDs. AFDDs are not required for EV charging equipment that conforms to BS-EN 61851. So this removes some of the uncertainty that was starting to build around whether this should be included. So the practical takeaway here is that EV charging design is becoming more integrated with the equipment itself. You need to understand what the charger is doing, what protection it already includes, and how that fits into the overall installation. Because if you treat it like a standard final circuit, you can easily overcomplicate it, or worse, misunderstand how it is actually protected. Power over Ethernet is now formally covered in BS 7671 under section 716. Before getting into the regulations, it's worth being clear what this actually is. This is where a single cable is used to provide both power and data. You will typically see these on things like CCTV cameras, Wi-Fi access points, and other networked equipment around a building. So what used to be just a data cable is now also part of the power distribution system. And that is why it now sits within the scope of the wiring regulations. The system operates at extra low voltage using self or PELV. And the regulations now go a step further in defining exactly how that supply must be provided. Regulation 716.414.1.1 sets out the permitted sources of supply for these systems. It must come either from a power sourcing equipment that meets the relevant product standards or from a source that meets the requirements for self or PELV, with a maximum of 60 volts ripple-free DC in dry locations and 15 volts ripple-free DC in all other locations. So although this looks like a simple data system, the safety of the supply is being tightly controlled at the source, so the voltage itself is not the main concern. The issue is current and heat. Regulation 716.523.2.101 limits the current in each conductor to 750 milliamps. That might not sound like a lot, but when you group multiple cables together, that heat starts to build up. And that has a direct effect on both safety and performance. As the temperature increases, you can get higher attenuation. What's attenuation? As the temperature decreases, you can get higher attenuation, which means the data performance of the cable can start to degrade. So how you install these cables now matters far more than it used to. Grouping, bundling, containment, all of these affect how the system behaves. Cable selection is also important. Regulation 716.521.101 requires cables to comply with recognized standards such as Category 5 or Category 6, and the same applies to the connections. Regulation 716.526.101 requires connecting hardware to be suitable for continuous current. So this is not just about making a data connection, it has to be capable of carrying power safely as well. There are also restrictions on where these systems can be used. Regulation 716.414.3.201 prohibits the use of self or PELV sources for ICT cabling in certain special locations. This includes bathrooms, swimming pools, saunas, and locations with restrictive movement. So even though the voltage is low, the environment still matters. There is also a functional earthing aspect. The cable screen may provide a form of functional earthing, but it is not suitable as a protective conductor, so it cannot be relied upon for fault protection. So the key change here is that data cabling is no longer just about communication. It is now part of the electrical installation, and it needs to be selected and installed with that in mind. This is an area that has caused confusion for a while. The regulation states that wiring systems shall be supported such that they are not liable to premature collapse in the event of a fire. That wording has often been misunderstood, and it has been taken to mean that the wiring system must remain operational during a fire. That is not the intention. This is where Amendment 4 makes a big change. Appendix 13 has been completely rewritten to support this requirement, and this is where the intent becomes clear. The aim is to not keep the circuit working. The aim is to prevent the wiring system from collapsing in a way that could obstruct escape routes or hinder firefighting operations. If a system needs to remain operational, that requirement sits elsewhere. For example, safety services under Chapter 56, and standards such as BS 5266 for emergency lighting and BS 5839 for fire detection. Appendix 13 now aligns more closely with Approved Document B and standards such as BS 9991 and BS 9999, and it introduces a more structured fire strategy approach. Instead of treating escape routes as completely clear spaces, it defines key areas, a point of relative safety such as a protected stair or firefighting shaft, and a point of ultimate safety which is outside the building. Cables in escape routes must not significantly add to the fire load, they must not emit large amounts of harmful gases, and they must not collapse onto occupants or firefighters. So in practice, this drives the use of metal fixings, fire-rated supports and appropriate containment systems. As you move into protected areas, the requirements become more restrictive. Only systems related to fire safety should be present, such as emergency lighting or fire detection. This also links into Regulation 422.2 and 422.2.2, which clarify how wiring systems are treated in protected escape routes and fire-resisting enclosures. There has also been a terminology shift in Regulation 421.1.7, where the term high-risk residential building has been replaced with high-rise residential building to better align with building safety legislation. There is also a link to Regulation 527, where a wiring system passes through a fire-resisting element. It must be sealed correctly. The opening must maintain the fire resistance of that structure. So this is not just about the cable itself, it is about how the installation behaves within the building during a fire. The way FI codes are used has been adjusted, and this has had a direct impact on how reports are produced on site. Previously, FI was closely tied to an unsatisfactory outcome. It was often treated as a default where something was not quite right, but could not be confirmed at the time of inspection. That has now been clarified. FI is no longer a classification of the condition itself. It is simply a statement that further investigation is advised because a proper judgment cannot yet be made. So if you can determine that something is dangerous, it should be coded C1. If it's potentially dangerous, it should be coded C2. Then we have C3, which is used where improvement is recommended. And this is where the intent behind FI becomes much clearer, because the model forms in Appendix 6 have now been updated, where C1 and C2 observations are now separated from C3 and FI in Section K on the model form. So how should we be using FI on the reports? FI only applies where you genuinely cannot reach that conclusion within the agreed scope of the inspection, and that brings about a wider change to how reports are structured. The extent of the installation and any limitations must now be agreed before the inspection begins. So if parts of the installation cannot be accessed or assessed, that is defined up front. FI is then used where the limitation prevents a proper assessment. So it is no longer a fallback, it is linked directly to scope and access. There is also a shift towards evidence. Regulation 653.2 now allows photographic and thermographic images to be included in the report. So instead of relying on assumption, you can now support your observation with actual evidence. That makes the report clearer for the client, and it makes your reasoning easier to justify. Appendix 6 is also more tightly linked to the reporting process. It is no longer just guidance sitting alongside the forms. It forms part of how the report is expected to be completed. So the practical change here is not just how FI is used, it is the whole reporting process is now more structured, more transparent, and more closely tied to what you can prove on site. Functional earthing is now formally set out in BS 7671 under section 545. This is not something new to the industry, but it has not previously been defined this clearly within the regulations. The first thing this section does is separate functional earthing from protective earthing. Protective earthing is there for safety. It is there to protect against electric shock under fault conditions. Functional earthing is different. It is there to ensure equipment operates correctly. Things like reducing electromagnetic interference, maintaining signal stability, and controlling electrical noise. Regulation 545.1.1 sets out how a functional bonding system should be arranged. Functional bonding conductors must be insulated. They must be installed separately from protective conductors, and they must only be connected to the main earthing terminal at one point. That is important. Keeping them separate prevents interference between systems. Insulating them recognises that they may carry current during normal operation, and having a single connection point avoids circulating currents. Where multiple functional conductors are used, the concept of a main functional earthing terminal is introduced. This provides a single control point of connection back to the main earthing terminal. Sizing is also handled differently. These conductors are not sized based on fault current like a CPC. They are sized based on the expected operational current, taking into account manufacturer's instructions. So this is driven by how the system behaves, not just a table of values. Continuity is also important. The system must remain intact even if equipment is removed for maintenance. And if a conductor performs both protective and functional roles, it must meet all the requirements of a protective conductor. So the key takeaway here is that functional earthing is now clearly defined. It has a specific role and it needs to be considered separately from protective earthing when you are designing and installing systems. P&B earthing is now formally recognised within BS 7671. P&B stands for Protective Neutral Bonding. It is not a new earthing system that you will go out and install. It is a type of supply arrangement provided by the network. In simple terms, the neutral conductor is connected to earth at a point between the transformer and the consumer's supply terminals. So instead of being earthed only at the transformer, it is earthed again closer to the installation. The reason for this is to reduce the risk of voltage rise if the PEN conductor becomes open circuit. If that happens, the installation can rise towards line voltage. Adding an earth connection closer to the building helps limit that rise. BS 7671 now recognises this arrangement, but it does not define how it is implemented in detail. That is covered by external guidance such as the ENA Engineering Recommendation G12. In real installations, this earth connection is typically made relatively close to the point of supply, often within tens of meters of the intake, although that distance comes from guidance, not directly from BS 7671. There is also an important distinction to understand. Where a system is supplied by a private network, PME conditions do not apply even if the arrangement looks similar. And where it is connected to a public network, the regulations prohibit the use of the neutral as a protective conductor within the installation, so you cannot assume it behaves in the same way as a TNCS system. So the change here is not that PMB is new, it is that it is now formally recognised, and you are expected to understand what type of supply arrangements are connected when you come across it. There are a few smaller changes that are easy to overlook, but they can make a big difference when you're actually using the book or working on site. Roman numerals have not been removed entirely, but they have been taken out of the main bullet points and replaced with standard lettering. You will still see Roman numerals used within indented lists. Another one to be aware of is how the changes are identified in the book. If you see a vertical line in the margin, this is marking where a change has been made. So if you are scanning through the regulations looking for updates, that is what you should be looking for. There have also been changes in medical locations, even though this will only apply to a small number of installations. Section 710 has been expanded to make requirements clearer and more defined. One of the key changes is around testing and verification. There is now a stronger requirement to record results, including functional testing of insulation monitoring devices and their alarms. So it is no longer just install and assume. It must be tested, recorded, and evidenced properly. There are also tighter requirements around bonding, with defined resistance values that must be achieved. So even though this is a specialist area, the expectation around testing and documentation has been raised. There is also a practical requirement around Caravan supplies. Regulation 721.55.2.6 now states that caravans must be supplied with a flexible cable that is at least 25 meters in length, with a minimum conductor size of 25 millimeters squared, and it should be colored orange. If you want to dive deeper into Caravan installation installations and how they are set up in practice, Joe Robinson has done a full CPD on that, and I've left links in the description. So what has Amendment 4 actually changed? It has not completely rewritten how you install electrical systems, but it has tightened expectations across the board. It has clarified areas that were often misunderstood, and it has brought modern technologies fully into scope. Things like batteries, EV charging, power over Ethernet, and systems with multiple sources of supply. So this is no longer just about installing equipment correctly. It is about understanding how the system operates as a whole, how protection behaves, and how different parts of the installation interact with each other. We do have a transitional period. There is a 6-month overlap where both versions of the regulations can be used. After that, the Brown Book is withdrawn and the Tangerine version becomes the current standard for new work. If you want to see what the IET had to say about these changes and hear their answers to some of the key questions coming out of Amendment 4, then click the video on screen now.